welcome back to me progressively going more insane as I have to redo each shoot 20 different times for the 2022 Practical Exam 3 MCQ. So question 31, this was one that's asking us to rank the potential energy of the spring at point Z, point Y, and point X using U of S is equal to 1/2 kx squared, x being the distance, k being the constant for the spring constant. So we know that this distance, d to z, when we stretch a spring here, it's actually going to be less than d. And we know it's going to be exactly d here for x. So it's going to be equal to d for x. Y, we can see that it's d here, so we're going to have two components. So we're going to have our x component is going to be equal to d, and our y component is going to be equal to d. So we know that overall it's going to be greater than x. So we can rank these as u of y is greater than u of x, which is greater than u of z. So our answer is going to be B. If I mess up in this video, I'll probably catch it and then I'll go back. So this video is going to be a lot longer than all the other ones. Because it is 11:04, I want to sleep and I don't feel like redoing each shoot a bunch of different times. Moving on to question number 32. Number 32 is a graph of projectile motion. So it gives us at time t equals 0 that a projectile is launched from the top of a cliff at an angle near 30 degrees below the horizontal. So let's draw this right here. Cliff launched right here at 30 degrees. And it gives us two pairs of graphs where displacement dx and the horizontal displacement dx and the vertical velocity component. So it's asking us to find the projectile. So it's asking us to find these two graphs. So we know that how our distance changed is just going to be linear. There's no horizontal acceleration. There's only horizontal velocity. So it's only going to move here. It's only going to move in a linear line. So that takes out C and D. Now what we have is our velocity for Y. The key word here is that it's launched. So that means that it starts with a starting velocity. So that means it can't be B because the velocity starts at 0. So our graph's going to look something like this. So our answer is A. Moving on to question number 33. Question number 33 asks us about the center of mass of momentum. So it gives us this graph right here, and it gives us 1, 2, 3, 4, and 1, 2, 3, 4, 5. So this dotted line right here is going to represent cart 1. It's going to be a linear line, and it's going to go from 4 to 1. Actually, it's going to be a little different right here. It's going to become a little more steeper. And then cart 2, it's going to be here, and it's going to plateau. This is in position, and this is in time. So, the question asks which of the following statements about the magnitude of momentum of the two cart system center of mass P of common is true. So, what we know is that P is equal to mass times velocity. So we know our mass is never going to change. The carts will always have the same mass, so we can take that out. What we do know changes is velocity. So our velocity is going to be equal to our slope of both lines, because P is going to be equal to the accumulation of both masses which doesn't change the same, doesn't change, so we can just write that as 1. We don't need to care about that. And it's going to be the velocity of cart 1 plus the velocity of cart 2. So at 2 seconds, we have velocity. We can just use our slope. So we can find the slope here. It's just 1/2 for the first one. So momentum before is equal to 1/2 plus 1/2, which is equal to 1. Our momentum after 2 is going to be equal to, now it's going 4 minus 2 in 3 seconds plus 0, which means we get 2/3. So our velocity decreases, and so P is smaller than it was before T equals 2. Therefore, our answer is B. There's a weird audio splice there. That's because I finally figured out that I could truncate videos in this editing software. I'm tired. Alright, moving on to question 34 now. Question 34 is about the change in kinetic energy of a sphere system. So it says sphere 1 is of mass m. It's right here. It's mass m. And it's connected like this. And then there's another sphere. And this one has a mass of 2m. So sphere 1 is pulled back and then is released from rest, and it's going to hit and it's collide with the second sphere. After this, it's an inelastic collision because they stick together. So we know that kinetic energy is not conserved, but momentum is conserved. Then it asks us, what is the change in kinetic energy of the two-sphere system? So first thing we have to do is we have to find the momentum of this before it hits and then during the collision. So we can just write that it moves with velocity 0, velocity I. So P1 is going to be equal to m times VO. P2 is equal to 3m Vx. So now we know we can just, these are equal to each other. So Vx is equal to 1/3 V of 0. So the kinetic energy of the system at the beginning, we can write is equal to 1/2 m V squared. And now it's Ke is equal to 1/2 times 3m times V squared over 9. Now if we do this, we get 3/2. Ke is equal to 3/2 m V squared over 9. That should not be a 9, that should be a 2. And then if that'll give us 3 over 18 if we multiply the 2 times the 9, which is equal to 1/6 mv squared. So now we just need to find the change in respect to Ki. This is equal to Ki. This is equal to, let's say, this is equal to Kf. So they're different ratios. So Ki, I'm going to rewrite that as here, 1/2 m v squared. So what we got to do here is we know this is equal to 1/3 Ki because it's 1/6 and that's 1/2. So Ki, Kf is equal to 1/3 Ki. So what we want to do now, since it asks for the difference, is 1/3 Ki minus Ki is equal to negative 2/3 Ki. And that's the answer, so the answer is D. Moving on to question 35. Question 35 is going to ask us about the average torque to slow down a wheel. So I'll write that once I get everything erased here. So it gives us a wheel with a radius 0.33 m, has rotational inertia 2.0 kg times meter squared, so I is equal to 2, and it gives us the angular velocity of 3 radians per second. Well, it's asking us for the average torque exerted on the wheel as it slows down from the magnitude. So what we're going to do here is we're going to use the equation rotational momentum is equal to moment of inertia times velocity. So we're going to get L is equal to 6. This is important because we're going to now use the equation delta L is equal to torque times delta T. Then we're going to divide delta L by delta T to get torque. It tells us that the wheel stops spinning after 6 seconds, so we know delta T is going to be equal to 6. And we know the change in rotational momentum is going to go from 6 to 0. So we get 6 divided by 6 is equal to torque. So we know torque is going to be equal to 1. So our answer is B. Now moving on to question number 36. Number 36 is asking us about 3 blocks. So there's 3 blocks on the surface, block 1 right here, block 2, and block 3. Block 1 is pushed with a force of P into block 1. 1, 2, 3. So this question is asking us what is the free body diagram for block 3. So free body diagram for block 3. First thing we can do is we can do gravity. We're going to do force normal. And I'm going to do force kinetic friction or static friction. Doesn't really matter. But now this eliminates a couple answers that could be. What we're going to look at now is we're going to have to choose between A and B. So in diagram A, it has 2 vectors pointing out. It has one for vector P and one for force of contact. This is wrong. P does not enact on block 3 at all. Because P is going to push on 1, and then 1's going to push on 2 at the contact force, but with that same force. But there's going to be friction here, so it's going to lose some force, and then it's going to push 2 is going to push 3 at this with even less contact force. So now we get F of C right there, and the only thing that matches with that is the answer C. Moving on to question 37 now. Question 37 is asking us about the force and net worked on a 2-block system, on a system that looks pretty much like this. There's a block here, pulley, and then there's a string around this, and there's a block in here. So the question reads, a block is set on a table where there's negligible friction between the block and the table. The block is connected on an identical hanging block by a lightweight string that passes over an ideal point as shown when the blocks are released, blah, 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 blah. What type of force or forces make a non-zero contribution to the network done by the two-block system? So what we need to do first is we just need to identify the forces. So we have the force of tension, force of gravity, force of normal, and force, and there's no force of kinetic friction. The gravitational force exerted by the Earth on the sliding block here is also perpendicular to the motion of the sliding block. So this motion here on the gravity is going to be perpendicular to how this moves due to tension. So no work is done on the sliding block, and the force of tension is inside a system of two blocks, and so the net work done by the tension on the two-block system is equal to 0. The only force that is doing work on the two-block system is the force of gravity exerted on the hanging block. So F of G is our answer. Gravitational force. Moving on to question 38 now. "38 is the force exerted on the floor by a bouncing ball." And so the question asks us, what is the amount of force exerted? Which of the following graphs below could represent the force exerted on the floor by the ball? And this is the graph we are given for the amount of force on the ball by the floor. And Newton's third law tells us that everything has to have an equal and opposite reaction. Therefore, the only answers that can be right are going to be C and D. D would give us the inverse, which is not what we want. We want the accumulation under the graphs to be equal at all times. So our answer is C. So in other words, if we write this as f of n, and this is delta as time, integral force dt for this has to be equal to the negative of the other force. Let's see, I'm just going to times dt. Now we will be moving on to question 39. Question 39 is about a system of two cards with different string tensions. So the diagram shows two different card systems. There's one where there's a string, and then it's attached to a block down here, and there's another one where they're attached by a spring. This one's a string, not a spring, my bad if I said spring earlier. And that's attached to a block here, and these are both attached to pulleys. So the question asks us, is the hanging block's acceleration as a function of time the same in both systems, why or why not? Well, this, we can do the potential energy to find, well, potential energy is going to be different for both of these, because there's gravity here, but the potential energy here is going to be in 1/2 kx squared. So to get this to move, you need to do more. And so the net force of the system is going to be constant for each, but when replaced by the spring is going to stretch and it's going to exert a changing force on cart X, and the tension of the string supporting the block Y will be different. Therefore, acceleration is not the same. If you need to remember anything, it's that springs and strings are not the same, ever. They are totally different. Potential energy for a spring is always going to be something like this. Potential energy for a string anything on the string is going to be MGH.